This video is a continuation on ANN discussion, particularly on neuron. The processing power of ANN can be explained through its most basic element, which is the neuron. The architecture of a neuron is shown here. It can have many inputs. Each of these inputs will have values coming into them. These inputs will also have weights associated with them, and neuron will first compute the weighted sum of the input signals. Weighted sum is the results of the summation of all input multiplied with their weights, and this weighted sum is represented as a capital letter X. Next, the neuron will compare the results of X with the threshold value theta to get the final output Y. For example, if the net input is less than the threshold, then the neuron output gets the result of -1. But if the net input is greater than or equal to the threshold, the neuron becomes activated and gets the value of +1. This final value is represented with capital Y. This is the action of applying transfer function, and the example above is called a sign function type transfer function. There are several types of activation functions. The ones that are most commonly used are step function, sign function, sigmoid function, and linear function. And the way or the function and how it works is as shown here. We have stated previously that intelligence in neuron is focused on its ability to learn and adapt. This capability was first introduced by Frank Rosenblatt in 1958, where he introduced the perceptron. The perceptron is the simplest form of a neural network. It consists of a single neuron that can adjust its weights with heart limiter. What this means here are the weights are changeable, but the heart limiter is constant. This is an example of a perceptron. It has two inputs, x1 and x2. Each of these inputs have weights, weight 1 and weight 2. The linear combiner will combine the sum of input times weight. This result, a capital X, will then be compared with the threshold or the activation function to get the output of Y. A heart limiter in perceptron is used to classify between inputs. For example, the graph in this slide is defined by this function. Anything that is mapped in this area belongs in the class A1, and anything that falls here belongs to class A2. So there is a straight line defining this function. How exactly a perceptron is capable of learning? It is through making small adjustments in the weights. The purpose of the adjustments is to reduce the difference between actual and desired outputs of the perceptron. For example, if a result of summation of input and weight falls under class A1 when it is supposed to be A2, the weight for that input will be updated. The initial weights are randomly assigned, usually in the range of -0.5 until 0.5, and then they are updated to obtain the output consistent with our training data. We talk about weight adjustment if actual result is not the same as desired result. To do that, there is a formula for calculating error, and this is the formula. Error is defined as desired result minus actual result, where P is the iteration. If the error result is positive, it means the actual result here is much smaller than the desired result. Therefore, actual result must be increased. However, if the error result is negative, it means the actual result is much higher than the desired result. Therefore, the actual result must be decreased. The objective of this is to get as close to zero as possible when it comes to error. Therefore, we come up with this perceptron learning rule. The weight of the next iteration is the weight of the current iteration plus alpha times the input of the current operation times error, where alpha is the learning rate. For example, if the current iteration is 2, the weight is 0.2, input is 1, and error is 1, alpha is given as 0.5. Because the error is not 0, we need to calculate the weight for the next iteration. Therefore, for P equals to 3, or the next iteration, the weight will be 0.2 plus 0.5 times 1, which is the input, times 1, which is the error. And we get 0.2 plus 0.5 equals to 0.7.